A pleasant day, everyone. Welcome once again to our discussion today. So, our topic for today is all about derivative of a function. Actually, this is just referred to our main topic, derivatives of algebraic functions. Okay, so before we go to the main topic, that is about slope, so let us make a quick review of what we had done in the past few videos. Okay, so before we have discussed this definition of the function, which is defined at each number x sub 0 in some open interval ab, the derivative of f at x denoted by f prime of x is given by the formula. Alright, so we have this formula which I derived last time. So just to make a quick review of this, so the condition here is that if the limit exists, so we can use this if this condition is satisfied. Alright, and then for the quick presentation of what we had last time about this formula that was derived from this illustration here. Okay, so I will briefly explain this one. Now we have this graph of our function, or the curves y equal to f of x, and we have this point here where one of the lines touches it only at this point. We call it tangent line, or LT. We denote this as LT. And we have here broken lines. Broken lines represent secant lines. We have LS. Alright, and we have here delta x. So what is this delta x? Delta x is the distance covered as on the horizontal line or along the x-axis as this point moves up going to this point P. Alright, at this point here, so we have delta x, short delta x, as it moves, the P sub 0 moves here, so we have a longer delta x, or if the point is here, so we have a longer delta x. Or if from point P, if we move this point P down this curve, along this curve, and as P approaches to P sub 0, we will see that delta x, as P goes here or comes here, the delta x is this one, right? And if the point moves here, then this is our delta x, right? And as this point moves closer to P sub 0, we can see that our delta x approaches to 0 as well, because at x equal to 0, x equal to 0 is the distance of P sub 0 from the y-axis, right? This is x sub 0. So at this point, our delta x equal to 0. So as point P moves along these curves, as P approaches to P sub 0, our delta x also approaches to 0. And we can see that our secant line moves closer and closer to the tangent line. Okay, so don't blink. I will show you quickly how these things happens, no? Just for a brief summary of what I was saying through the graphical illustration. Okay, it's something like this, class. So you watch as the point moves down, approaching P sub 0. Watch also the secant line approaching LT and the delta x approaching 0. Okay, so something like this. Alright, now as P moves closer to P sub 0, our secant line now is getting closer to LT. I'll make it bigger for us to see clearly. Okay, so we have formed here triangle. Okay, so this is our reference now when we calculate the slope. Okay, so if we are going to move this point P much closer to P sub 0, say at this point here, alright, at this point, so we can say that this secant line will be very near, or perhaps it will touch the tangent line. Okay, So, or in short, we can say that as point P moves closer, very close to P sub 0, our secant line will move closer to tangent line. So we can approximate that as this point P moves at this point, then the secant line will be this line, right? Touching or very close to tangent line. So we have here a small triangle, right triangle, which is the basis of our calculation of our slope. Okay, but at the moment, we'll just consider this bigger triangle here. Okay, so that we can have this as our delta y, or the difference between these two value of the functions. Okay, and our delta x, this one. Okay, so I'll go quickly to the next, this one, these slides. Okay, so to recall, we have this, from that illustration, we have derived this formula of the derivative, okay, as delta x approaches to 0. So we have here function of, this is the value of the function, x sub 0 plus delta x distance from point 0 or p sub 0. Okay, now the derivative of a function at a number x can also be defined in different but equivalent ways. So how to do that? We have first, we let delta x equal to h. So if we let delta x or change delta x to h, so what will happen to this one? Okay, so we have here delta x is changed to h. Alright, so retaining the other items. Okay, now second is if we let delta x equal to the difference between x and x sub 0, then in other words, you have to change delta x here with x minus x sub 0. So the formula, this formula will become something like this. So this time it's less complicated to see. So what was the things done here, why it becomes like this? Okay, so this is the illustration class. Alright, you change delta x to x minus x sub 0. So second step, change delta x to x minus x sub 0. So this one changed to x minus x sub 0. So we have this. And we have here x sub 0 positive, then we have negative x sub 0. So combining them, what is left? Only x. So that's why we have only f sub x here. Then just retain it, right? So you just copy it. At the denominator, instead of delta x, we change delta x to x minus x sub 0. So that's why we have x minus x sub 0. Alright, now the third step is if you change x sub 0 to a. So very specific, our x sub 0 is equal to a. So the formula becomes like this. So instead of f prime sub x sub 0, we have f prime of a equal to the limit of f of x minus f sub, instead of f sub x sub 0, we have f sub a. Then divided by x sub, instead of x sub 0, we have x sub, x minus x sub 0, we have x minus a. As x approaches x sub 0, so now we have x approaches to a. Okay, so this is now our formula that we're going to use. Alright, so now let's solve some example. So this is the long method class of finding the derivative. There will be a shortcut on this. I will discuss that later on when we discuss the differentiation rules. Alright, so for example, if you are given here this function f of x equal to 2x plus 3. So can you remember, this is our example number 1 in one of the videos, short videos that I uploaded. And then we have the answer here, that is f prime of x is equal to 2. So how it becomes like this? So this is the solution that we have done, class. Alright, so what we did here, we just simply change the x, change x to x plus h. Right, we just change x to x plus h. Alright, so changing x to x plus h. So what happened? Okay, so we have here x to x, so change x to x plus h. Alright, so we have changed x to x plus h. So that's why here we have rx. So this is rx, x plus 2h. So 2x, so 2 times x or x plus h, then plus 3. So plus 3 minus f of x. So f of x, the whole thing is 2x plus 3. So minus this. But take note, there are two terms here, so you have to enclose this with a parenthesis. That's why we have 2x enclosed with a parenthesis. Alright, because you have this matters plus the sign here if this is negative. So that's why you have to enclose with a parenthesis. If this is not included or enclosed with a parenthesis, your answer will be wrong. Okay, so divided by h. So limit as h approaches to 0, limit of this function. Now, distributing 2 and multiply it to each term of the quantity inside the quantity. Okay, so we have 2 times x, so we have 2x. 2 times h, so we have 2h. Then plus 3. Then here, you distribute negative. Understood, there is a 1 here, negative 1. So negative 1 multiplied by 2x, so we have negative 2x. Negative 1 multiplied by 3, so we have negative 3. So divided by h, so limit of this function as h approaches to 0. Now, combining similar terms, you have 2x, we have minus 2x. So you combine them, 2x minus 2x is equal to 0. We also have positive 3 minus 3. So 3 minus 3, 0. So what is left at the numerator is only 2h. Okay? At denominator, we have h. So we have now limit of 2h over h as h approaches to 0. So h divided by h, this is equal to 1. 2 times 1 equal to 2. So that's why we have the derivative of the function is equal to 2. Right? So I hope you still remember, no? This is what we have discussed in the video. Right? Okay, so this is our answer. Okay, so that was our first example class. Then our second example was something like this. Okay, so we have another given here. So find the derivative of, we have function of x equal to x squared plus 3x. Okay, so the rule here is just simply change x to x plus h. So we got the answer f prime of x equal to 2x plus 3. So how did we solve this problem last time? So it's here the solution. Now this is the one that you have seen in the video. So you're given f of x or function of x equal to x squared plus 3x. So again, you just change x to x plus h. So we have here x. You change that x plus h, then that is squared. So you also have to square. And then you have 3 times x. So 3 times x, ang x natin, we change it to x plus h. Then minus f of x. Now from the formula, we have minus f of x. Alright, so f of x natin is x squared plus 3x. Okay, so again, our f of x is composed of two terms, so you have to enclose this with a parenthesis when you subtract it from this part here. Then divided by h, so limit of this as h approaches to 0. Okay, so when you expand this one, this is a binomial, so expanding this first term here, so the rule is you have to square the first term. Okay, that is your first term here, plus twice the product of the first and second term. So that's why you have 2 times xh. Then plus h squared, you have to square the second term. Okay, and then you multiply 3 to each term of the quantity. So you have 3 times x, so 3x, plus 3 times h, we have 3h. Then minus, again, this is understood to be have a 1 here. So negative 1 times x squared, so you have minus x squared. Then negative 1 multiplied by 3x, so you have negative 3x. So negative 1 multiplied by 3x, so you have negative 3x divided by h. Okay, as h approaches to 0. Now again, combining similar terms, at the numerator you have x squared, you have minus x squared. So x squared minus x squared, that is 0. you also have 3x, then you have minus 3x. So 3x minus 3x equal to 0. So what is left at the numerator is this one, which is 2x squared, this one, which is h squared, and you have 3h, and divided by h. So limit of this as h approaches to 0. Okay, now at the numerator, if you look at this closely, you can see that there is a common of its term, that is h. So what you're going to do is to factor that common, which is h. So you divide its term by the common factor. So 2x h divided by h, so we have 2x. H squared divided by h, we have h. 3h divided by h, you have 3. So divided by h. Now you have the common factor, which is h. Denominator, you have h. So h divided by h equal to 1. So what is now the function is becomes 2x plus h plus 3. So as limit approaches to 0. So now when you substitute h by 0, so you have now 2x plus 3. So we have this derivative of function x, or f prime of x, equal to 2x. So this is the answer that we had obtained last time. Okay, so that's the second example. The third example was something like this. We are given here a function that is in radical form. So f of x equal to square root of x. So the answer for this one is, this is the answer, 1 over 2 square root of x. So again, this is the solution. So same thing, class, you just change x to x plus h. You change x to x plus h. Okay, so changing x to x plus h, so your x here must becomes x plus h, because you change x to x plus h. Then minus f of x. So from the formula, you have minus function of x. So our function of x, y is a function of x, that is square root of x. Okay, then after that, if you look at this one, class, it is composed of a radical. So the technique here, if you meet or encounter this kind of given, so the best way to solve this is to multiply both numerator and denominator by its conjugate. So conjugate means if this is minus, so you have to multiply by the same thing but plus at the middle. If this is plus, the conjugate is minus or negative. So that's why we have here, you just copy this part here, okay, and then multiply it by the conjugate. Conjugate of the numerator is square root of x h plus square root of x. So that's why we have it here, the conjugate. Then what you did in the numerator, do it also at the denominator, so that we are not changing we're not violating any rule. So we are not changing anything. We are not changing the function here. So it's just the same, because this thing here over the same thing, so that is equal to 1. Alright? So after that, you multiply, multiply each term, the first quantity, with the first term, and second term, the second quantity. Then second term, the first quantity multiplied by each term of this quantity. And then we have rule of multiplication. We have to multiply the numerators and we have to multiply the denominators. So evaluating this, or multiplying these numerators, so we got this, okay, and denominator you multiply, so we got this. Then after that, since these two, x plus h square root and square root of x plus h, so you multiply these two, so you can put them together in one radical or one square root, and then you just square them, because x plus h, it has 2x plus h here and multiply it, so you have 2 of that. And take note, if this is square root, it means that the index of the radical is equal to 2. Your exponent is 2, so that cancels out. Or it's just like having x plus h squared, then raised to the power 1/2. So the rule is, from the low exponent, if you have 2 exponents, you just multiply the exponents. So 2 times 1/2, that becomes 1. So you have x plus h, okay? So no more square root, no more square. Alright, then minus. So same here. You have this part here, class, they are just the same. You have this product. This is positive, this is negative. So this becomes 0. So what is left is these two terms here. This term and this term. Alright, so we have evaluated this already. Okay, then you have x squared. then square root of x squared. So that cancels out. So divided by h multiplied by same denominator, the conjugate. Then equal to, so I put the equal sign here, limit of, so as h approaches to 0, so this is now x plus h. Okay, so after evaluating, so this becomes x plus h, right? Then you have here, do the same thing here. From the low exponent, you have x. Square root of x times square root of x is simply x. Okay, so you have x at the numerator, you have minus x at the numerator, so x minus x is 0. So what is left at the numerator is only h. Okay, so you have only h. At the denominator, you have h, and so on. And then you have h at the numerator, h at the denominator, so h divided by h is equal to 1. So that's why we have it here. The limit y prime, or the first derivative, is limit equal to the limit of 1 over square root of x plus h plus square root of x. Now, as h approaches to 0, so change h to 0. So square root of x plus 0, so that is still square root of x. So that's why we have a square root of x here, plus 0, plus square root of x. Okay, so you have 1 divided by square root of x plus square root of x, or it's just like 1 divided by 1 square root of x plus 1 square root of x. So you have 1 divided by 2 square root of x. So this is our answer. Y prime equal to 1 divided by 2 times square root of x. Okay, so that was the example last time, and then we just add this, or I think we have this already also in our video. So the added example number 3. Alright, so that's all for the sort of review, and then we go to the main topic for today, that is about the slope. Okay, so before that, we have this explanation class that the derivative of function at a number x can also be defined in different but equivalent ways. Okay, so I think we have discussed this already. Just to recall, to summarize everything, and then to continue, we have here remarks from that statement in the previous slide. So the remarks here are the following. So from the definition and example, we see that the derivative of function is also a function, and that function is denoted by a prime of x. So have you noticed, class, when we solve the derivative of 2x, or the one that is having squared, x squared plus 3x, so when you take the derivative of that function, the resulting derivative of that function is also a function. So this is what is explained here, that from the definition and example, we see that the derivative of a function is also a function, and that the function is denoted by a prime of that x. And the domain of f prime is a subset of the domain of f. Alright, so it's sort of just part of the domain also, subset. Subset, if you can still remember what does it mean by subset. So the domain of the derivative of the function is the subset of the domain of the function f. So we have here another definition, just to make a summary of everything about the derivative. So the definition is like this, class. The process of finding the derivative of a function is called differentiation. Okay, the process of finding the derivative of a function is what we call differentiation. Okay, if y equal to f of x, or y a function of x, the derivative of f can also be denoted by something like this. Y prime equal to, or this is equivalent to dy over dx. So we have so many symbols, class, used, like the one that I discussed in the other videos. Okay, so we have even the Euler's notation, something like this. So this also indicates derivative. And we also have something like this, as you have seen in the previous slides. Okay, Now, geometrically, so this time class will talk about slope. So geometrically, the derivative of a function at a number x sub 0 is the slope of the tangent line. If you can still remember, no, at the beginning of our discussion, we talk about slope of the tangent line as the secant line approaches to tangent line. So we form a triangle, which is the basis of our calculation for the slope or the derivation of the slope. Just to recall a little bit. So we have this kind of illustration a while ago. Okay, so slope. So what does it mean? So again, I'll just illustrate the geometric figures that we have discussed at the beginning in this slide. Okay, so we have formed this triangle here. We just assume that the P is up to here, or P can move farther, so that the secant line will really very close to tangent line, and we will use supposedly this triangle here, the smaller right triangle here. But for the sake of our discussion, so that it can be seen clearly, so I use this bigger triangle, and we have this as our delta y. Delta y is the difference of the height of the functions, and then we have here delta x. Okay, so from the definition, we have slope is equal to the rise over run. It means that our rise here is delta y, our run is delta x. Okay, so that's a slope. Okay, so delta y can be calculated as the difference between this height for the function here, that is f sub x sub 0 plus delta x, then minus this height f sub x sub 0. Okay, so the difference of these two, you subtract this by this one, that is now our delta y. Okay, for delta x, that is from here to there, meaning the distance from the y-axis towards this point, that is x plus delta x. Then distance from this point from the y-axis to p sub 0, that is x sub 0. So the difference, x plus delta x, sorry, x sub 0 plus delta x minus x sub 0. So what is left is delta x. So that's why we have delta x here. Alright, so the slope is calculated from this illustration class. Okay, so if you can still recall from our analytic geometry, or even in our discussion previously, we have the slope m, the slope formula, we have delta y over delta x, or we have m equal to y2 y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So this is our definition for the slope. Okay, now since y is a function of x, then m is equal to function of x sub 2 minus function of x sub 1 divided by delta x. X sub 2 minus x sub 1, that is the difference. So the difference is, that is delta x. Okay, also delta x equal to x sub 2 minus x sub 1. So m must be something like this: f sub x sub 1 plus delta x minus f sub x sub 1 divided by delta x. So that is now the formula of our slope. Now if you take the limit of that, okay, if you take the limit of that ratio, okay, so the limit of f sub x sub o plus delta x minus f sub x sub o over delta x as delta x approaches to 0, so that would be the slope of our tangent line. So MTL here means slope of the tangent line at x sub 0. Okay, so that is the calculation or the derivation of the slope of the tangent line. Now we have here one example, and after this I'll cut this video and then I'll give you more example in the other video. Okay, so first find the slope of the tangent line of the graph of the given function x squared at x equal to 1. Okay, so to solve this, so same thing class, we have to use the long method. Alright, you just change x to, this time instead of x, change x to x plus h. So this time we change x to x plus delta x. Okay, So slope of the tangent line of x is equal to the limit of f sub x plus delta x minus f sub x divided by delta x. Okay, so now we change, as mentioned, change x to x plus delta x and then evaluate. So in our previous example class, we changed x to x plus h, but now in this example, this topic about slope, so we change x to x plus delta x and then substitute. Okay, so we have the function x squared. So our x is x plus delta x, so we have x plus delta x squared. Then in our formula, we have minus f of x. So our f of x is x squared, so minus x squared. Then divided by delta x, the limit as delta x approaches to 0. Now expanding this one, this is also a binomial term or binomial expansion. So expanding this binomial, so we have square the first term, x squared, twice the product of the first and second term, you have 2x delta x, then square the second term, which is delta x squared, minus x squared. So at the numerator, you have x squared, okay, then minus x squared, so combining them, that becomes 0. Okay, so what is left is that we have 2x delta x plus delta x squared. Okay, so if you look at these two, there is a common. So what is a common there? That is delta x. So factor out delta x. So when you factor out delta x, so here at the numerator delta x, okay, so this is the common factor, so factor it out. So the first term, what is it in the first term is 2x, and then the second term would be delta x. Alright, so this is our new function now. And at the denominator, we have delta x. So delta x at the numerator, delta x at the denominator, so you can divide. So delta x divided by delta x, so that becomes 1. So therefore, you have the limit. Okay, and class, don't forget to write the word limit. You don't have to do it directly. So in your solution, you have to, so you have equal here. Okay, then you still write limit. Okay, limit of this function as delta x approaches to 0. Okay, alright, so as delta x approaches to 0, so what is left? So this one, nothing, so 2x plus delta x, so therefore you have 2x plus 0, or your final answer is equal to 2x. So this is the slope of the tangent line 2x. Now at x equal to 1, so what is the slope at x equal to 1? Slope of the tangent line. So this is the solution class. Slope at x equal to 1 is MTL, so 1. So at x, okay, at x equal to 1, so equal to 2 times, because our slope here is 2x, so 2 times x, or x equal to 1, 2 times 1 equal to 2. Okay, so that's it. That's the first example of the slope. I'll give you more example on this part, slope of the tangent line, on our next video. Thank you very much. Thanks for watching, and see you again in the next video. Please stay safe and healthy always. God bless, and bye bye for now.